Hello, so my name is Gerecht.
And I'm Michael Winchester.
And so our project was on the analysis of muon flux across altitude in conjunction with the UNC DemoSat program. So I bet the, come on, there we go. So I bet a lot of you are wondering, well, what the heck are muons? Well, they're a form of subatomic particle, and they're actually close cousins of the electron, well, close being relative. If you look at this table, we have the electron. They have a mass of about 0.511 mega electron volts, which is the unit we use for stuff, very small stuff moving very fast. And whereas muons have a mass of about 106 mega electron volts. So muons are about 200 times the size of an electron, and yet they still have the same -1 charge. So because of this, that means that muons are not affected by other matter like electrons are. So they don't go into orbit around atomic nucleuses. They usually just go straight by because they're too heavy to be pulled. So, but they don't last that long. Like electrons, they're always here. They're always but muons, they decay after about 2.2 microseconds. And after those 2.2 microseconds, they're no longer here. So they're only a brief visitor.
So with that comes, where do they come from? And up in the upper atmosphere, there are cosmic rays which are created by supernovas and the sun and other explosions in the upper atmosphere. And when the cosmic rays impact these atomic nuclei, they create pions. And these pions decay very fast into muons at about 14 kilometers in the atmosphere. And as they keep coming towards Earth, they decay into neutrinos with a negative charge.
So the muon flux is basically, well, flux is basically the number of muon occurrences within a certain area within a certain amount of time. So at sea level, muon flux is about 1 muon per square centimeter per minute per steradian. And a steradian is basically just a 3D angle measurement. So, because these cosmic rays hit the Earth from all sorts of angles, so you need something to clarify which angles they're coming in from. So, this is a very helpful graph conducted from, derived from an experiment from the University of Southern Arkansas, also on muon flux. So they tested theirs on a number of different locations, and as you can see down here, like from 60 feet underground, they barely got like 50 counts per minute. So that's not a very high muon flux. But as they go up, you can already see that the muon flux is increasing. So look at that last altitude, the 4,200 feet. Does that kind of sound familiar to anybody? Because the altitude of Greeley, we're up here about 4,500 feet. So that's mostly what you can expect as a baseline.
So for our experiment, we're sending up the payload with a weather balloon that will go up 30 kilometers to collect the muon count as the elevation increases and decreases when the balloon goes up and then pops and falls back down here. And so our hypothesis is the muon count will dramatically increase as the balloon floats up and the elevation increases. The muon count will be significantly higher, and then it will drop, and there will be a sharp decrease after 15 kilometers. Because the atmosphere here closer to the surface is a lot less than as you go higher.
Yeah, 90% of all the atmosphere gases is condensed down here, basically at the bottom layer. So past 15 kilometers, there's almost nothing. So we're predicting that there's not going to be any collisions that would create muons. So methods. So we had to construct a payload module that would carry our Geiger counter up there and at the same time survive the conditions that are present at 30 kilometers. So we'll get more into the materials in just a minute. So these are just some views of the box. So that's the almost completed box minus all the electrical equipment. So we have a bunch of thermal insulation and a PVC pipe that goes straight through the center, which will be the anchor point for it on the flight string of the balloon.
As for the hardware, we have the basis for the structure, which is made out of foam core, and that's the sort of box-like thing. And that just serves as the basic structure for our payload that will enclose all the other stuff inside. And then next we have the fiberglass insulation, which keeps everything inside heated and warm, because up at 30 kilometers it gets very cold, and so we want to keep everything inside working and heated. And the Mylar rescue blanket is another layer of insulation, which reflects the IR heat radiation, so to also keep everything warm inside. And then the aluminum tape just improves the aesthetics of the structure, and it is another layer of insulation.
So what's the point of having a very nice and warm box if you don't send anything up in it? So front and center is our Geiger counter. That is a SparkFun Geiger counter. The Geiger counter itself is actually just a small tube up here. So within that tube is basically just two small electrodes separated by a short distance, and the whole tube is filled with an inert gas, typically argon or helium or some other form of noble gas. So it doesn't react very much. When an ionizing form of radiation, such as muons in this case, enters the chamber, it briefly charges that gas and completes the circuit, which registers as a single count. So we just count the number of those per minute to get our main data. In addition to that, we also have a VMP 180 sensor. It's really simple. All it does is measure temperature and pressure, and from pressure we can derive the altitude. So the data from both of these sensors is wired to an Arduino board, which you may remember from the earlier robotics presentation. It's just a very simple microcontroller, easy to program, easy to use, and of course lightweight. And that's a very big concern for payload. And once the Arduino processes all information, it's sent to the micro SD shield, where it's stored on an SD card. The card itself is not very big. The card fits into that little rectangle on the right side there. So it's not very big, not a lot of data storage, but it's more than enough to get everything that we need.
So as for heating the payload, we constructed a heater which is made up of 1 kilo-ohm power resistors, which are up there connected to the breadboard is what it's called. And we soldered those onto there so they would stay in place and not move around in the payload too much when it goes up. And then to get all the electricity to the heaters to provide the heat, we have 8 9-volt batteries, which provides all the heat. And this is a circuit diagram that shows the electricity and how it will heat the heaters. And then we have 4 batteries, and those are in series. And then the 2 sets are in parallel. And the switch to make sure that we turn it on right before we send it up, because we don't want to be wasting power before we launch it.
So we'll just go through this briefly. You have to make sure that the payload module will work up at 30 kilometers, because if it shorts out or freezes up, we're not going to get any data. So the whip test, again, this is real simple. All you do is just put the flight string through the PVC pipe and then swing it around really fast. If anything breaks, you know that you didn't do something right. Drop test is probably the simplest one on here. All we did, take the box, take it up to the roof, throw it. Done.
So the next test is the elevator test, and this was to test the VMP 180. So what we did was, here in Ross, we took our sensor and Arduino to collect the data, and we went to an elevator, and we would go to each floor and walk around a little bit, go back to the elevator, and then continue to go each floor and do this to test the sensor so we could see if it worked and provide sufficient altitude and the data. And then our last test was the temperature test, and that was to see if the heater could provide sufficient heat for the module for the entire duration of the flight. And so that is a graph that we put the whole module in liquid nitrogen and in a box, styrofoam box, and the liquid nitrogen was a lot colder than what it will be up at 30 kilometers. The liquid nitrogen temperature is about negative 196 degrees Celsius, and up at 30 kilometers, the temperature will range from about negative 80 to negative 90 degrees Celsius. And so testing with dry ice would have been a lot, simulation a lot better for the test, because dry ice is about negative 80 degrees Celsius.
But as far as this graph goes, real quick, the green line, that was a temperature probe that was right next to our heater, so you can actually see it gain temperature early on. Orange one was from temperature probe that was inside the payload box, but not next to the heater. And the blue one was just an ambient temperature, and we may have accidentally touched it 1 or 2 times. So, but
So we did a hike with the Geiger counter to Spearhead Peak, which was a hike from 1,500 meters to 3,600 meters, and that is like nothing compared to how high the balloon's going to go up. 30 kilometers is about 100,000 meters up. So we just needed to test the Geiger counter and get data for that, so we could test it and make sure it works.
So this is the data that we gathered during the hike. So as you can see, right here, this is us and Greeley, and so the counts per minute, they kind of are in the range between 30 and 15, but they kind of average out to 20. But as you can see, as you got higher and higher during the ascent, the average counts per minute increased until we have an average about 60 counts per minute up here. So one thing I want to quickly address too is that you'll know, if you remember that other graph I showed you at the beginning, you'll notice that they had counts well above 2,000 kind of. Well, I have two explanations for that. One is that the other experiment likely had more sophisticated equipment that had higher detection rates. The other one is that this hike was completely at night. So almost all of this data was gathered during nighttime, and so that would limit the amount of muons produced from our own sun that would come in. So, but still, there's a clear upward trend. So what possible implications could the fact that there's more subatomic particles that you've never heard about up at higher elevations have? Well, as I think I mentioned before, muons are a form of ionizing radiation. So in ionizing radiation, what that means is it has the chance to knock a electron off of a DNA sequence in an organism and cause a mutation. So I should just point out real quick, these can be good mutations or they can be bad mutations. It's arbitrary. Before everyone starts freaking out, muons are part of the cosmic of the background radiation that we're exposed to about 100% of our life, and they only make up about 10% roughly. So if you're really going to get up in arms saying that muons are going to cause cancer or whatever, I'd look at this 50% down here first before you start worrying about muons. And also, this is kind of really just looking into the far future, as we don't have a lot of data and we don't have a lot of ideas. But potentially, you could use the muon flux to record altitude or have just a second form of altimeter, since our current ones rely on pressure, and that can easily be skewed by weather systems or other things. So it can be used as an alternate form of that.
So the next step for our thing, we will launch the balloon in about a week, and we'll send it up, and then we'll wait 3 hours for it to follow that or come down. And it'll be like storm chasers. We have to go find it, get the SD card back, and then we'll go get all the data, record it, and we'll figure out how to like read it and get the actual results. And that'll be again 30 kilometers up.
So these are just our references and acknowledgments. So we'd just like to really quick thank Dr. CMAC and our mentors, David and Amber, for all the hard work that they put into our project. And
I'd like to thank Excel Energy for sponsoring the research. It was a lot of fun working with David and Amber creating this module, and it was a ton of fun, and I couldn't have had this much fun anywhere else.
And I'd also like to thank my sponsor, the Adolf Coors Foundation. Thank you. Without you guys, I wouldn't be here right now. And finally, we'd also like to thank Lori Ball and all the other FSI staff, Chris, Topher, or Jess, Maurice, and everyone else for making this such a great summer. So that's it.